Hello, my name is Siddhartha Vadaparty. I am a junior who attends Montgomery High School, New Jersey. In this video, I'll be talking about my iSTEM research project, which I've been working on for several months now. My independent research project focuses on circular motion. Like all aspects of physics, this subject should be handled quantitatively and qualitatively so that way students, such as myself, get the best insight as possible. Unlike linear motion, where an object doesn't change direction, circular motion focuses on an object which is continuously changing direction. This makes it extra hard for students to learn, and makes it even more important that they learn it properly. In this video, we'll be looking at an apparatus that I built in my independent research project that will enable students to easily collect data on circular motion and derive relationships from the data. I hope you enjoy the next 20 minutes with me. Rotating frames, like the one seen next to me, have been the interest of physicists, students, and teachers alike for decades. Multiple demonstrations have been given throughout these years, like the classic film Frames of Reference by Professors Hume and Ivy, to the contemporary video Rotating Frames of Reference by MIT Professor Sharma. However, while these demonstrations provide helpful visual aids, the best way for students to learn physics is to perform hands-on experiments and derive the relationships for themselves. Unfortunately, the equipment available for observing rotating frames are prohibitively expensive. For instance, one set can cost up to $800 just for all the parts included for one experimental setup. Additionally, forces like the centrifugal and Coriolis force are not properly explained or demonstrated to students in these experiments. To address the issue of affordability and ease of hands-on experimentation, I have built my own DIY platform, the Cirkinemeter. We will address, throughout this video, the experiments that this platform can perform on rotating frames, and how we can use it to demonstrate the rotating frame's laws of physics. Additionally, we'll look at the Cirkinemeter itself and see how it is able to work. The rest of this video will be divided into 3 chapters, each with its own more specific demographic. The first chapter introduces frames of reference and distinguishes between non-inertial and inertial frames of reference. Chapter 2 introduces the Cirkinemeter as an experimental equipment and shows the kinds of experiments students can use it for on rotating frames. The third and final chapter analyzes the electronics and housing of the Cirkinemeter and shows how they interact with each other. In order to understand rotating frames, we first must understand what a frame of reference is at all. In the scope of this video, the frame of reference is defined as 3 orthogonal axes, like seen here, where they're labeled X, Y, and Z. These axes are such that any point is measured with respect to these axes. From here, we can then define displacement, velocity, and acceleration, and the rest of kinematics. That means these frames can be placed anywhere, whether it is stationary on Earth, like as seen in my hand, or on a rotating disk, as seen before. Seen below are 2 frames of references that are identically oriented and have a steel ball that is stationary to both of them. These frames are what are known as an inertial frame of reference. Because no force is acting on the ball will continue to be stationary relative to both frames and will not move on its own. This follows Newton's law of inertia, that no object shall change its motion unless acted upon by an unbalanced force. Now, let's look at the frame on the disk while it's rotating. Now, the frame on the disk, as seen here, is rotating. However, the ball with respect to this frame still remains stationary. This frame, however, sees the ball as moving in a circular path, and also accelerating. Because this frame is accelerating with respect to this frame, which is an inertial frame as established earlier, we call this rotating frame a non-inertial frame. This means that any object that moves in this frame will experience non-inertial forces, forces that do not have an apparent source. Now we see how big a difference that our frames of references make when observing objects moving. But how do we know that this rotating frame violates the first law of inertia? Now we'll see if there is a way to determine if one is on a non-inertial frame or on an inertial frame, based off of solely an object's behavior. Even though the surrounding disk appears stationary, we see the ball and string accelerate outward on their own, without any inertial source of acceleration. This leads us to believe that we are not, in fact, on an inertial frame of reference, but rather a non-inertial frame. However, we should perform more than one test to confirm this hypothesis. As seen in the previous demonstration, the ball moved outward on its own, so therefore we can't be in an inertial frame of reference. To confirm this, let's roll a marble across it. If this really is an inertial frame, then the marble should move in a straight line. The marble curved. There is some force causing it to take a counterclockwise turn. So we're not in an inertial frame, but what frame are we in? We were in a rotating frame, so non-inertial as we suspect. The marbles were rolling across this rotating disk, and the motor was responsible for causing it to spin. And the apparatus is Arduino-based. Now we've made a setup where we can confirm whether the marble's moving in a straight line. We've placed two boxes diametrically opposite of each other, and we are viewing through two different frames, an inertial frame and a rotating frame. We'll now roll a marble and see how the paths compare between the two. The right-hand screen shows that the marble moves in a straight line, as Newton's law of inertia would predict. However, the left screen shows the marble curving on a clockwise rotation, and therefore it does not follow the law of inertia. That is why this and other accelerating frames are called non-inertial frames of reference. We've now set up the equipment so that way it will capture the inertial motion and rotating motion in one go. To represent the marble, we're using this marker and drawing it across this diametric linear path. The ink trace it will leave behind will reveal the path that the marble takes in the rotating frame. Let's take a closer look at the path made by our marker. The path seen here represents the path that our marble would have taken in a rotating frame. Starting here, our marble seems to take a clockwise rotation in contrast to the counterclockwise motion of our disk. This is because at every point in our marble's motion, there is a perpendicular force acting on it, causing it to take this loop. This force is called the Coriolis force. The existence of the centrifugal force has been a source of confusion for many. Even now, popular sources disagree on whether or not it exists at all. While Khan Academy says that it doesn't exist at all, especially in good reference frames, the American Journal of Physics says that it exists, but only in the rotating frame. So how can we confirm which is valid and which is not? To determine the direction that forces act in, we'll first look at how gravity affects our accelerometer. Right now, we have our phone attached and live streaming the data that we are measuring. First, we have our accelerometer with the z-axis pointing out of the table. Looking at the z-axis data, we observe that the acceleration measured is approximately negative g, meaning it's a downward acceleration that we are experiencing, which matches our predictions of how we observe gravity, which always pulls down. Now, when we rotate the accelerometer such that it is the y-axis facing up, we'll observe that the y-axis approaches a g value instead. The acceleration also is indicated to be pointing downward, as we predict. Finally, when we rotate the x-axis to be pointing upward, we get an acceleration that's still pointing downward. In order to prove or disprove the outward centrifugal force's existence, we're placing the x-axis of the accelerometer towards the center of the disk. If we measure a negative acceleration along this axis, that means there must be an outward force pulling on the accelerometer. Looking at the x-axis acceleration data, we see a negative value. This means, through direct measurement, we confirm that there is an outward force acting on the accelerometer in the rotating frame. This means the centrifugal force is, without a doubt, very much real on the rotating frame. Now, we know that the Cirkinemeter can measure the centrifugal force, but how can we use it to also find a relationship between its parameters, radius, and omega? The Cirkinemeter can measure three kinds of data: the radius length that you place the accelerometer on, the acceleration felt by the accelerometer on the rotating disk, and the angular velocity at which the disk rotates. The Cirkinemeter is equipped with many ways to measure data. For instance, on the rotating disk, there are multiple concentric circles with radii lines on every layer. This means you can actually experiment with the radius that your accelerometer measures at. For instance, you can measure it from here to here. On top of being able to measure the acceleration and the radial length that our accelerometer is at, we can also measure the angular velocity of the rotating disk. Through our joystick on our motherboard, which we'll get into more detail later, we can control the speed of the disk, starting at very low to faster, to incredulously fast. Back down to slow again. Thanks to the Cirkinemeter, students can directly measure the centrifugal acceleration, the angular velocity, and the radius length. Through these measurements, students can derive the mathematical relationship between the three variables. If we look at the graphs given, we notice that the data collected very closely matches the data expected for the same inputted variable. The experiments we can perform go beyond the centrifugal and centripetal forces, as we can even document the Coriolis force on a polar graph. Using this marker to represent the marble moving across the diameter, we'll see what path it makes in the rotating frame. We can even experiment with the rolling marble's speed. This time we'll about half the velocity of the marble rolling across the diameter. After marking the Coriolis acceleration on polar graphs, we used Professor Stein-Ross's and Professor Ivy's equations to see whether they matched up with the expected values. The graphs remarkably match. These graphs were made using a free online software called Desmos, which allows people to graph in Cartesian coordinates, like x-y relationships, or polar coordinates, r in terms of theta, or in parametric equations, x in terms of t and y in terms of t. For these graphs, we use parametric equations where we use them as coordinates. Looking at the expected and actual graphs for the first experiment, we see a remarkable similarity, as both have a single teardrop-like shape. From the perspective of someone fixed to the rotating frame, it would appear as if a marble rolled from the edge of the disk towards the center and then slowly back out towards the same location. Looking at the second experiment's expected and actual graphs, we see an additional similarity. However, unlike the first trial, the half-speed marble appears to make an open loop, where it goes towards the center, makes a similar teardrop loop, and then goes to the opposite end of the disk. We have now seen that the Cirkinemeter can perform multiple experiments on rotating frames. We will now look under the hood, if you will, of the Cirkinemeter to see what parts make it tick. It can be divided into three main components. The first component is what we call the motherboard. Its purpose is to measure the angular velocity, control the speed and direction of the motor, and publish the data it collects. The second component is an accelerometer, which directly measures the acceleration felt on a rotating frame of reference. The third and final component is the laser cut housing, which provides a skeleton for the entire platform. Now, let's examine these parts in more detail. This is a fully assembled motherboard inside its 3D case. Now let's open it up and look at its parts. The motherboard, the first of the three parts of the Cirkinemeter, has three fundamental components: a modified Arduino microcontroller, an H-bridge, and a 2-axis joystick. We used Adafruit's Feather, a 32U4 microcontroller, as the central control for the calculations and logic-based actions. It runs on 3.3 volts of logic. The OLED wing is used to display angular velocity and the revolutions per second. Its pin arrangements allow it to be plugged in directly into any member of the Feather family. Pololu's TB66 H-bridge acts as a voltage amplifier, able to supply up to 12 volts for the motor instead of 3.3 logic volts. It's also the circuitry that enables the motor to switch direction and control its speed. Adafruit's 2-axis joystick utilizes two built-in potentiometers. This allows the user to manually manipulate the speed and direction of the motor. When it moves up, it increases the speed, whereas slowing it down causes it to decrease. However, changing the joystick's position horizontally changes the disk's direction. For instance, right is counterclockwise and left is clockwise. This is a fully assembled accelerometer inside its 3D case. Now let's open it up and see the parts. The accelerometer also has three components: a Feather host, an accelerometer chip, and a Bluetooth antenna. In this version of the platform, we also use the 32U4 microcontroller for the accelerometer. It receives data from the accelerometer chip and then sends it to the Bluetooth antenna. Adafruit's LIS3DH accelerometer can measure the acceleration on three different axes, labeled X, Y, Z, as seen. The HC06 Bluetooth antenna enables the accelerometer device to publish the acceleration measurements to smartphones. This complements the growing use of smartphones in educational environments perfectly. When the disk is stationary, the X acceleration starts off at around 0. However, as I increase the revolutions per second, the x-axis acceleration increases as well. And when I decrease the RPS, the acceleration also decreases. The last major component of the Cirkinemeter is the laser cut housing. It has three main regions: the upper region designated to spinning disks, the lower region designated to holding the motor in place, and the IR brake beam sensor designated to timing revolutions. The upper region is where the user can perform experiments on circular kinematics, like the ones seen earlier. The top disk is marked with several concentric circles of various labeled radii. The next region is the IR sensor pair. The receiver is outside of the housing, while the transmitter hangs underneath the spinning disk. When the receiver detects the transmitter, the receiver then sends a signal to the motherboard, which then records the time. Now, let's look at the lower region. The lower region provides space for the motor to securely fasten to. The motor rests on a small mount. This mount is directly attached to a large rectangular base, which has screw holes in each of its corners. Combined, these components create the Cirkinemeter. It can both visually and numerically display the angular velocity. Additionally, the Cirkinemeter can directly measure the acceleration, allowing students to derive the relationship between acceleration, radius, and omega. And finally, it provides a platform to demonstrate the Coriolis force on. All this content is probably a lot to digest, so let's break down quickly what we just learned. Inertial frames are frames that obey the law of inertia, while non-inertial frames are accelerating frames that do not obey the law of inertia. The Cirkinemeter, the equipment we use throughout this entire video, can qualitatively and quantitatively measure the Coriolis force and centrifugal force with a high degree of accuracy. The Cirkinemeter runs on open-source Arduino-based technology. What I bet you're wondering is, what am I trying to accomplish? Well, my goal was to accomplish two things. First, to provide students a fun and easy way to learn the laws of circular motion. And two, create a platform which students can easily modify to perform new experiments which might not have been performed in this video. The main microcontroller of the Cirkinemeter, the Arduino, is everywhere on the public domain. This means students have easy access to information on how to use the Arduino and how to modify, therefore, the Cirkinemeter to their own liking. By making the equipment open source, I'm granting students the purest form of science, the ability to design experiments. I hope you enjoyed this video. Have a good rest of your day.